So to finish our day, we're going to take a more careful look at the activity series and kind of a silly story that I think will help you kind of make sense of it, or at least get to the point that you can use it pretty easily. That pivot activity combined with the single replacement practice got you two different activity series. One of them is the activity series for the metal, which you picked up during the pivot activity, and then I gave you a green one and you added that to your resource sheet. Your resource sheet is getting bigger and bigger. The one that you're going to get for your test will look like yours. That's got the extra pieces glued onto it. So you don't have to memorize that activity series, you just have to know how to use it. The other activity series you picked up while doing your single replacement reaction practice, and that's the one that goes with the nonmetals in the column that's called the halogens. I don't have to include that one on your resource sheet because if you look at the periodic table, the halogens piece is just in order, top to bottom, in the second to last column of your periodic table. So I don't have to put that on your resource sheet because it's already on your periodic table. There are two ways to think of the activity series. The activity series is there to help us answer the question, will the reaction happen? So we ran into this for the first time with the copper and the silver. We did two different scenarios. One where we had silver ions and we had copper atoms, and we were able to turn the copper atoms into ions and the silver ions into atoms, and we were successful. And then we had our failed reaction where we had the copper as ions and the silver as atoms, and when we put those two things together, nothing happened. One way to look at the activity series is to look at it in terms of the more active of the two elements will be an ion when the reaction is complete. So when we looked at silver, which is at the bottom, and copper, which is two steps up from the silver, the reaction was going to be done when the more active of the two elements ends up as an ion. Copper is the more active of the two elements, so when the copper wasn't an ion to start with, the reaction could go forward. But when we started with copper already as an ion, like in reaction number 2, we were already in the condition where the more active element was an ion, so there was no reason for the chemical reaction to go forward. We were just plain old stuck. Now that's a lot to think about because it's got a lot of chemistry in there. The alternative way to think of it is to think of a kind of silly dating story. You can think of the activity series as being essentially a popularity contest between the elements. The elements at the top are chemistry studs, and the elements at the bottom are chemistry duds. And so the rule is that the stud always gets the date. The more active element can push the less active element out of the compound. Or in other words, the more active element gets the date. So let's imagine it's back in the fall and it's homecoming time. Lead and nitrate show up for the homecoming dance together, having enjoyed a lovely dinner. Aluminum comes into the dance alone and is thinking, it sure would be nice to have somebody to dance with. So aluminum approaches nitrate and says, hey nitrate, wouldn't you rather be with me? And nitrate looks at its situation and says, well gee, I'm currently with lead, but now I have an opportunity to be with aluminum. And aluminum is quite the stud compared with my current date. You know what, aluminum? That seems like a really good idea. Bye-bye, lead. And so lead suddenly finds himself without a date, and the aluminum has weaseled its way into the compound. And that reaction occurs because aluminum is a bigger stud than lead, and the stud gets the date. And now there's some balancing that we have to do to get the chemistry to work out, which doesn't really fit so well into the dating story, but the big thing is to use the dating story to figure out if the reaction occurs. Well, this worked out fabulously for aluminum. So aluminum gets to thinking at prom time, you know what? I don't really feel like paying for dinner, and I had this worked out really well for homecoming. So prom season rolls around, and aluminum again shows up at the dance with no date. Nitrate has enjoyed a beautiful evening out to dinner with magnesium, and aluminum sees the lovely nitrate at the dance, and aluminum swings on over and says, "Hey nitrate, wouldn't you rather be with me?" And what does nitrate say? No. Because nitrate won't pick aluminum over magnesium, because magnesium is up here, and magnesium is a bigger stud than aluminum. No reaction. I find that to actually be the easiest way to think about single replacement reactions. Chemistry studs and duds, and the stud always gets the date. Not exactly chemically sound, but it is a way to get the job done. It's no different when you're thinking in terms of the halogens. In the second to last column of the periodic table, we have these four nonmetals. Fluorine is chemistry's big stud. Fluorine always gets the date. Iodine is chemistry's big dud. Iodine never gets the date. And just remember that when single replacement reactions happen, elements have to push out one of their own kind. So here, the fluorine would be trying to push out the iodine by saying, "Hey potassium, wouldn't you rather be with me?" And what does potassium say? Heck yeah! You are the biggest stud of them all. Goodbye, iodine. So iodine's out on its own. Always have to balance our equation. Well, that really made iodine angry. And so a week later, iodine sees that fluorine is hanging out with lithium, and iodine thinks, "I'm going to give fluorine back. I'm going to exact revenge here." And so iodine comes wandering over and says, "Hey lithium, would you rather hang with me?" And lithium says, "No way. Sorry, iodine, you're a big dud. I'm not going to give up my stud to be with you." In the middle of the series here, we have chlorine and bromine. And so one fine day, lithium is hanging out with bromine when chlorine approaches and says, "Hey lithium, wouldn't you rather be with me?" And lithium says, "Yeah, you bet." Plus fluorine comes along. And that's really all there is to the activity series. It's just a question of who gets the date. And that's what we gain from that little experience. So let's look now at your homework, which I have linked at this point to our agenda. I've got the key linked there, but we're going to kind of walk through this together. All right, so this first one really just had you looking at reactions that take place and reactions that don't. You had some little videos, and you had to come up with an activity series for the halogens. And you probably noticed that chlorine always gets to be in the compound. Iodine is always displaced, but displaces nothing, leading you to stack them, chlorine, bromine, iodine. And then the thing that we can kind of infer is that if that's in stack order on the periodic table, that the fluorine must go at the top of the stack, because that would be the logical pattern for this to follow. Number 2 had you look at an explanation of this little novelty toy called a citrus clock, where you take any piece of citrus clock you want, or citrus fruit that you want, you stab a piece of zinc and a piece of copper into the clock, the electrons move between the zinc and the copper, routing through the clock, and it makes the clock work. So after watching this video, I just wanted you to explain why it is that the zinc moves its electrons toward copper rather than copper moving electrons toward zinc. And it's because the zinc is more active than the copper, so it will lose the electrons to become an ion more easily than what copper loses its electrons. And in any pair of metals, the more active element will be oxidized, the less active metal will be reduced. So in order to be oxidized, those electrons have to leave zinc and go in the direction of the copper. You could just as easily make the clock from magnesium and aluminum. Since magnesium is more active than aluminum, magnesium will be oxidized, aluminum will be reduced. remembering that in any pair of metals, the more active metal will be oxidized or become an ion, the less active metal will be reduced, and it will be an atom. In number 3, we're trying to add some things to our activity series. So we're given some reactions, and we're told that these things do occur. So this is a reaction where silver is able to push gold out of the compound, and silver gets the date. If silver can steal gold's date, that means that silver is more of a stud than gold, and so gold must end up at the bottom of the activity series. Gold is chemistry's ultimate dud. Now, if you look at the bottom of your activity series, you will see that humans like the duds of the chemical world. Down there at the bottom are the things we consider to be valuable: gold, silver, copper. As humans, we like those things because they don't want to give up electrons. They don't react with stuff. Gold never rusts, but your car does. Nobody wants an iron necklace because over time, your necklace will rust. A gold necklace or a silver necklace doesn't want to give up any electrons. So we as humans value those duds of the chemical world because they don't react with stuff and become tarnished or corroded. So gold is definitely going to go at the bottom there. That. Get this stuff out of our way. And then we start looking at cadmium. And we have 2 reactions here that involve cadmium. In the first reaction, iron is able to get the date from cadmium. So there's cadmium. If the iron can take cadmium's date, iron is more active than the cadmium. In the next one, cadmium is able to push lead out, which tells you that cadmium is a bigger stud than lead. So we know lead goes below the cadmium. And in our activity series, the one I gave you, there's nothing between iron and lead. So we know that cadmium has to slot in between the iron and the lead. Question?
I think I found an activity series somewhere that had platinum on the very bottom. Is that correct, or is?
Yep. Platinum would go below gold if we had a complete activity series.
Okay.
And it too is considered to be one of our precious metals that doesn't oxidize very easily. So in the end, our activity series, if we take all the new pieces we had, get all this junk out of our way, ends up with the cadmium slotted right in there between the iron and the lead, and the gold down at the very bottom. And if we were in fact to go searching some more, we would find out that platinum goes actually down at the bottom. It's an even bigger dud than gold, and in fact is worth a little bit more per ounce than what gold is. Okay. Bottom flat picture of the reaction between silver and gold nitrate. Here's my gold nitrate, all dissolved. Here's my silver atoms. Each silver atom pushes 1 electron to the gold, leaving me with a gold atom and 3 silver ions. Number 5, we're supposed to decide, will this take place? So, will gold be able to take cadmium's date? Having established that gold is a big dud, no way nitrate's going to give up cadmium in order to be with gold. And lastly, we were to make a prediction about what would happen if we threw some aluminum into some copper 2 chloride. And here's our picture. To save us some time, I just did this back at the office and took a picture. So hopefully you predicted that we would be able to form copper solid and that the aluminum would turn into ions. So over time, what will happen is that our aluminum foil will disappear and our copper ions will turn into copper atoms, and so we'll end up with copper instead of aluminum when all is said and done.
Are all of those chunks there solid copper?
Mm-hmm.
That's a lot of copper.
It is a lot of copper. I used kind of a big beaker and rather a large piece of aluminum foil. Wanted it to photograph nicely. Then the last thing I want to look at is this Pivot Interactive. The very last question seems to have caused people some problems. So this very last one, where we had to figure out what metal ion was in the solution. So here is kind of a bigger activity series for us. I think it's easiest if we kind of approach this from either the top down or the bottom up. Like doing it in just the random order that they gave us, you end up with something that doesn't really make a whole lot of sense. So since magnesium is of all the metals we have is at the top, I'm going to stick the magnesium right there for a second. Now I'm going to react mystery metal solution with the magnesium. And if we fast forward, we can see that mystery metal reacts with magnesium. So if I take magnesium, we're just going to call it mystery metal. So we'll give it MM for now for mystery metal. And maybe it's mystery metal nitrate. Magnesium is able to get the date. Hold tight, crew. We got 2.5 minutes left. So magnesium can take mystery metal's date. Does that say mystery metal goes above magnesium or below magnesium? Below. So I know that mystery metal goes down here. Could mystery metal be magnesium? No. Because something will not react with itself. If the metal reacted with the magnesium, it's safe to say that the metal isn't magnesium. So we know that it's not magnesium, and we know that mystery metal goes below magnesium. Okay, so we'll pull up our list. We don't have any aluminum, but we do have some zinc. So we'll load up our zinc next. So this time around, we're looking to see if zinc can replace mystery metal. Oh, and look here, we are getting a chemical reaction. We're getting some junk along the edges here. So we are successful. Zinc is able to replace mystery metal. Do I put zinc above mystery metal or below mystery metal? It's up here. Okay. And again, mystery metal can't be zinc because zinc is reacting with mystery metal. Okay, then I don't have any cobalt or tin on my list, but I do have some lead. So let's run a check with some lead. So I run this whole thing with lead, and I find out it does not react with lead. So it's got to end up between zinc and lead, and I think the only ones there that fit the bill are either cobalt or tin. Now, in theory, it could also be lead, because lead wouldn't react with lead, except that in the earlier simulations, lead nitrate was one that you had, and lead nitrate isn't colored at all. So we can kind of eliminate the lead just because we saw some earlier, and this solution is definitely kind of orangish pink, and we didn't see an orangish pink one earlier. So I think you can get as far as saying it's either cobalt or tin, but we can't make the final decision with the information we have in terms of whether it is cobalt or it is tin.